right, we are going to talk about, hello sir, spectroscopy and the electromagnetic spectrum. Where are you going to be? Oh, there it is. Yeah, I understand where I'm supposed to sign it. I'm trying to figure out when you're going to be gone.
That was good. That was good.
I don't know that I'm going to have stuff ready for you beyond what we have done.
I know, I really like the movie.
I gotta sign it here. There it is, sir. Sorry. All right. Spectroscopy, electromagnetic spectrum. Remember when we're talking about the electromagnetic spectrum that we have a visible light. If they give you something, a diagram like this, you need to be very careful, okay? Typically, this diagram can either be done this way where they've got gamma rays at this end, but sometimes you'll see it, and more commonly, I would even say, where you've got gamma rays over here, okay? My point is that get your orientation right, okay? Make sure that you're at the right spot on this, okay? Remember, these are called ionizing radiation. So this radiation here can form ions, cause electrons to pop off where they shouldn't, and thus you end up with cancer, okay? UV, you can handle a little bit of that, and you can handle more of that than you can X-rays. X-rays, you can handle more than you can gamma rays. All of these, you can handle some of. Okay, you're getting gamma rays right now. The bricks in the wall, the soil from the underneath us, gamma rays are coming at you right now. But it's a very small amount. And, you know, organisms are capable of being able to deal with small amounts of that. It's when these get to the extreme that you have problems. You get too much of this, you're going to have problems. What is infrared? Heat. Okay, you get too much heat, you got problems. You get too much microwaves, you're gonna have problems. Okay. Huh? Yeah, I mean, it would be too concentrated. Yeah, I mean, no, that's fine. The food is fine. It's what you're doing with that food is you're taking the water molecules and you're vibrating them. And that vibration is then producing heat. Just like when you vibrate your hands back and forth, move them back and forth, you're generating heat. The same thing happens with the microwaves. Okay. Your cell phones actually communicate via microwave. That's how your cell phones get data from the towers. Okay. And then there's radio waves. Okay. And these are just the different waves that you get, you know, that are across this spectrum. There's actually waves up here called cosmic rays that are even higher up. But we don't come into contact with those typically here because we have an atmosphere that protects us from them. You will have a little bit of minor exposure to those when you fly because you're up way up where you have very little atmosphere above you. So you go up to like 36,000 feet. So, you know, that for a while they were a little concerned about pilots and stuff like that, people who typically spend a lot of time in that vicinity. But I'm, you know, as a mom of a pilot that spends a lot of time up there, I'm not really concerned about it. It's not something that I'm like, oh my God, I have a kid. He can't go into that profession. He's going, you know, I'm not worried about it. So, and I worry about everything. All right. Now, molecules can move in different ways. Okay. And you're going to have to memorize some of this stuff. Okay. But it's not hard. I will show you some examples. Okay. So molecules move in different ways as transitional movement from one place to another. They can have rotational, which is spinning in place, and they can have vibrational, which is moving in place. The movement of the atoms within the molecules is relative to one another, such as bending, stretching, and internal movement of the molecules. Okay. Oh, why is this not advancing? Come on. Why are you not moving? All right. Huh? What was that? Well, it shouldn't be Wi-Fi because this is directly connected.
Yeah, Carl's Jr. was having issues with the Wi-Fi.
You don't even have a Carl's Jr. here. What?
He's talking about Denver Hughes.
What?
He calls Denver Carl's Jr. for some reason. Why?
Oh, weird. All right. Molecular motions, vibrational, rotational, and transitional motions of CO2 are illustrated here. Only a perfectly ordered crystalline substance at absolute zero would exhibit no molecular motion and have zero entropy. Is this going to happen in your lifetime? In the presence of you? No. So in practice, this is an unattainable ideal. All right. What do you need to know? Microwaves exhibit rotational levels. How do you remember that? Well, what do you have in most microwaves? You have a rotating plate, right? So that's how you associate microwave and rotational, because in the microwave, that stuff goes around. So connect those two things in your brain. All right?
So like every time they talk about microwave, you always know rotational.
It's rotational. Yep.
Yeah.
Okay.
Where's this?
Typically, they will ask you something like, you have rotational, molecules present. Which form of radiation caused this? And they'll list like 4, and you would pick microwave. Okay.
Rotational only in microwave?
Okay. Remember that. Infrared is vibrational. Just like if you vibrate your hands back and forth, you generate heat, and heat is infrared. So remember vibrational, infrared.
I'm still waiting.
These are how they determine that, and this is beyond my level. You're never going to see this. I'm just showing you this graph. When you get into college, you may be playing with these. They can look at this data, and they know from this type of data what kind of bonds are present. So way above this course, you don't need to worry about it. Okay? This is what they're talking about as far as stretching and that sort of thing. All right. UV to visible light then. These are going to be transitional. So they will cause electrons to transition from one level to another. And remember what happens when they go up? They must come down because they're unstable. Remember that? I talked about climbing a ladder. We have our ground state. When these things get excited by energy in the form of electricity or heat, they climb up those levels. And then they fall back down to get back to the ground state because they're unstable. When they fall back up, down, what do they give off? Light or energy. Okay? And you can look at those transitions and be able to determine what material you're dealing with. Okay? So visible spectroscopy, these are going to be typically in these nanometers as far as the wavelength is concerned. UV is going to be smaller, and these are going to cause transitions of the elements. Okay? We can look at these transitions and be able to tell what's going on by using one of these spectrophotometers, which will calculate or be able to measure the wavelength of that light that's coming off. Okay, and that's what we're going to look at when we get to Beer-Lambert. All right, so we've got spectroscopy. We've got 2 samples. Sample 1 absorbed twice as much light as sample 2. What can you deduce about the concentrations? Which one would be darker then? Let's start with that. 1. Okay, so this would be darker. So if you have a darker sample, what does that indicate about the concentration? It's higher concentration. You remember doing that lab where you had to do the serial dilutions up here? The blue all the way across? Some of you. Some of you.
So what did we say
You never took yet.
This is more concentrated. Sample 1 is more concentrated than sample 2.
What must be true?
In order to be able to get this, the solutions have to have some sort of color to them. So in order to make this happen, you have to have some sort of color to your sample. If you don't, and it's all clear, it's not going to look any different concentrated versus not. You can't look at hydrochloric acid and just say, oh, that one's more concentrated than that one, because it's clear. So you have to have a colored sample to make this work. Describe the type of changes that occur within the molecule during the process of UV, vis spectroscopy. That is going to be transitions. The electrons are going to be transitioning from one electron level to another.
Okay. Are we doing the we do or are we skipping it?
Apparently we're skipping it.
Okay.
All right. Photoelectric effect. We have, we've covered this in regular chem, but this is essentially where if you shine a light on a metal, it ends up popping electrons off.
Why?
Because light acts as a particle, and sometimes it acts as a wave. In this case, it's going to act like a particle, and it's going to be able to move those electrons off. Moving electrons are the definition of what? Electricity. Okay. So we can harness those electrons that are coming off of that metal, and that's how they create solar electricity. And that's how your solar calculators work. That's how the solar arrays, these solar farms that you're starting to see out at a lot of different places, that's how those work. Okay. Because light is composed of photons. Remember, the energy of that photon is equal to Planck's constant times. Anybody remember what this is? It's not a V, you guys. Yeah, it's a Greek letter nu. It's not velocity. Nope, it's not velocity. Is 2 is 2 is 2. Is 2 is 2.
Oh, wait, frequency.
Frequency. There it is. I told you it was on there. You didn't believe me. Yes, this is the very first equation that actually is listed on this table. So the very first equation is that guy. And then off to the side, they tell you what those symbols represent.
I like the wavelength symbol. It looks like a
That is lambda. Wavelength is lambda.
Kappa. Gamma. Alpha. Sigma.
All right. The photoelectric effect then is based on that light having wave-like and particle-like properties. Einstein was the one that kind of brought that all together. We talked about the photons. We can measure the amount of energy needed to remove those electrons, and that is our minimum energy. That is also known as the binding energy. Greater energy values indicate that electrons are closest to the nucleus, or that the nucleus is a higher charge. So here, for example, if we had red light, remember red light carries less energy than blue or violet light. So here, we don't have enough energy. We haven't met the threshold of the energy to be able to pop those electrons off. Our green light does, so that works. And then our blue light is even more energetic, so it's going to move those electrons even faster. Okay. If a frequency higher than the threshold energy is used, the electrons will be ejected with more kinetic energy. Here's your V. This is your velocity here.
I don't like it.
As opposed to nu. Do you see the difference between nu and V?
I prefer acceleration.
All right. The amount of energy needed to eject an electron can also be thought of in terms of the longest wavelength that will still eject that. And that would be the wavelength max. And any waves that are shorter than that will not have enough energy to eject the electron. These are the equations that you need to be concerned with. H is Planck's constant. This is your frequency. We have this guy. We can actually solve for frequency, and then which would be C over lambda, which we can then substitute C over lambda in for energy. What? So the total energy of the light is equal to the kinetic energy of the electron that was ejected. The energy then to remove the electron is a work function for the substance phi, and the work function differs for different materials. So certain things will work better than others. All right, summary of the photoelectric effect. The energy of the light must meet a minimum energy. That's called the threshold frequency, or having a shorter wavelength that if the minimum energy is not met, we're not going to be able to move the electrons. The rate of the emission of the photoelectrons is known as the photoelectric effect. Photoelectric current then is proportional to the intensity of the light. The more intense the light, the more electrons you're going to get. And lastly, if the minimum energy is met to eject those electrons, the kinetic energy of the photoelectrons is dependent on the energy of the light to eject those electrons. This was back when you guys couldn't use calculators. We're going to skip that. We don't need to worry about that anymore. You can use calculators now.
I got a calculator.
This guy you might want to know about though. Okay, so let's talk about him.
No, he's
One conversion factor that you need to be familiar with, and that is not on your constant sheet, is that 1 meter equals 1 times 10 to the 9 nanometers. So if your wavelength of your light is given in nanometers, you have to be able to convert that into meters. Yep. So just remember this guy, okay? You don't need to worry about this anymore because you can use your calculator to do this. This was back before you couldn't use calculators, so I should take that out now. You used to not be able to use calculators on multiple choice, but they removed.
Yeah.
You're the first generation that gets to use
Matthew
calculators.
cried. He's like, big MM cried. He's like, oh my.
All right.
Oh my calculator.
So when a metal surface is exposed to light, the electrons first begin to be ejected from the metal. And the energy of the photon is this. So this is the minimum threshold energy that we can have work for us, okay? They want to know what the frequency is. Well, if this is my equation and I want to solve for frequency, what do I have to do? What is frequency equal to? Energy divided by H, okay? So my energy is 3.3 times 10 to the negative 19 joules. My Planck's constant is 6.626 times 10 to the negative 34. You are not expected to have that memorized. It is on your constants and equation sheet. What happens to my joules? Yep, they're going to cancel out. That's going to leave me with units of 1 over seconds. 1 over seconds is hertz. Okay. All right. Get out my handy dandy calculator. Clear. 0.3 negative. Remember, there's a difference between negative and minus. And I ended up with 4. Oh, wait a minute. I need 2 sig figs, so I got to round that. Hold on. So this is going to end up being 5.0 times 10 to the 14th. All right, now I need to calculate wavelength. So if I have this equation, How do I get wavelength by itself?
Divide by the frequency. C.
Yep. So I'm going to go lambda equals C over nu. I'm going to take the speed of light again on your constant sheet.
Okay.
I'm going to grab my frequency from up here. Now, let's say that you got this value wrong. What's going to happen to your answer down here?
Your answer is going to be wrong.
It's going to be wrong, but if you calculate it correctly based on that bad data, they will still give you the points.
Right.
Mhm.
WBR.
That's why I grade the way I do. That's why I do that, because that's what AP does. That also means that if you have no flipping clue how to do this step here, or write a number down, okay,
Genius.
you will lose points here. But if you know how to do this step, you'll still get these points. Okay. It doesn't matter if you put down 5,000 here and use that down here to do your calculation. If you do that and you get this answer right, they will still give you credit.
Wait, so should 5.0 times 10 to the 14, should that be labeled with an S or with hertz?
I screwed that up. Hold on. This would be 1 over seconds. And this would be meters per. Oh, that second was down there. That was from this. That was from up here.
Oh, okay.
That was from that guy. And then I got sidetracked and never gave you. So this comes from the speed of light. I'm trying to make it bold so you can tell the difference between. This is from the speed of light, these units, meters per second.
Oh.
Okay. And this second comes from down here, inverse seconds. Better? Makes sense? Okay.
Yes.
So these are going to cancel out. That's going to leave me with meters, which makes sense because,
This wavelength.
yep. Okay. So now I'm going to take my wavelength or my speed of light, and I'm going to, so that's alpha C, and divide by that frequency.
What is the answer?
And I end up with 2 sig figs, so 6.0 times 10 to the negative 7th meters. Yep. Okay. So this is my answer for this guy. Now they want to know the color of light. The problem is, though, that this is given in nanometers. So I need to take this guy. I need to put him into lovely dimensional analysis, which I know all of you just love and adore.
Oh, so much.
Times 1e to the 9. 600.
Okay. So I ended up with 602 for my nanometers. So then I'm going to go here and find where that falls. So my light would be orange.
When asked questions
Orange.
like that on the AP test, do we need to write it in a complete sentence?
No.
Or we just write
No, you
Orange.
never do.
Just making sure.
Orange.
Unless it says justify.
Yeah, if it's justified, then you need to explain it, but you don't even have to do it in complete sentences. Like, just get to the point. Okay.
Are we doing the beer Lambert law too?
We're going to start in on that.
But that's not due until.
The lab is not due until Wednesday. Or
What?
The end of class Wednesday, right?
Yeah.
Is it-
Okay, I want to talk about Beer Lambert because I want to talk about your lab next week. Okay, because you're going to have some stuff that you need to do over the weekend for that. All right. So 13 in this packet, I want everything done by the 31st in the packet.
Okay, I have a question. There's this little, after 3.10,
There was that weird sheet, yeah.
this sheet, you know, let's do it.
I don't know. I'd have to see it closer.
I can bring it up.
I'm guessing that solubility, and the answer is going to be a definite yes.
Solubility and precipitation.
But I'm also giving you until the 31st, which is a week from Monday, to get it done.
It's
and you guys have days off. So yeah, you guys need to do this for sure. Yep. And Matthew, you may need some help with that because this is stuff that they've seen, but you never have.
Oh, we have seen. Oh, man, I'm back.
All right. Beer Lambert. This is where we're going to spend all next week. Okay. So one way that we can measure the concentration of a colored solution, and that's the key, this has to be colored, is by seeing how much light can be passed through or how much light is stopped by the solution. A more concentrated solution will absorb more light. Okay. And from that, then you can tell what the molarity is of the substance. All right. So when we look at these, we've got these cuvettes here. Okay. This is what these are called. And you're going to have them in a box. If your cuvette can't be cleaned, then you just throw it away and get new ones. But in your box, you should have these cute little cuvettes. Okay. You should only clean these with something called a Chem wipe. So do you see I've got Chem wipes up here at the front? Those are Chem wipes. They are specially designed tissues that do not scratch plastic or glass. If you use the brown paper towels on these, they get little scratches. And even microscopic scratches can affect your data. So that's why these should only ever be cleaned with the Chem wipes and water. You have to get, I don't know if you can see that there's a bunch of water spots on this guy. I don't know if I put it up against my shirt here. Can you see the water spots on there? Yeah. Okay. You have to have those gone. They will affect your data. Okay. They're going to absorb some light. They're going to prevent light from getting through there. Okay. It's kind of like a translucent window. You know, not as much light gets through as if the window was just completely glass, like clear glass. So you've got to get rid of those. Any fingerprints will cause a problem. Water droplets actually magnify the light and make it appear less concentrated. So there's all of that stuff will affect these. So you've got your cuvettes here. These cuvettes have little lids on them. And I expected the lids to be in place before these get put down in the spectrophotometers. These spectrophotometers are about $600 a piece. Okay. So I don't want any liquid, the possibility of liquid getting spilled in here. So make sure that you have these capped and cleaned before you put them down in here. All right. This guy, this sits on the table like this, but I'm going to turn it like this so I can show it to you. Okay. This guy is where you're going to insert your cuvette. The light beam is shown through here. Your cuvettes have two different types of sides. They've got one side that has ridges on it and one side that's supposed to be clear. The ridges are where you put your fingers. So you need to get, you're going to get fingerprints on these. That's your ridge side. So your fingerprints have ridges. The sides of this have ridges. That's what you want. When you put this in, you want the clear sides facing the light bulb so that the light will go straight through the cuvette. Okay, and make sure this is sitting down flat. Okay, does that make sense? You are going to have a blank in there. The blank actually has distilled water in it, so it's not completely blank, but it has distilled water in it, which should not have any color. If you put distilled water in here and it has color, you need to go back and clean the thing. Okay. And then you're going to have a series of dilutions with copper nitrate, starting at 0.2 is your stock solution, and then getting less concentrated as you move down to your blank. Okay. So when we are doing this, you're going to have different colors. Different colors absorb differently on this. Okay. So if, for example, you had orange in your if your solution was orange, then that means that that solution is absorbing what kind of light? Why is it showing as orange?
It's
Oh, it's
absorbing.
absorbing. Yeah.
Exactly. Yep.
Yes.
It's reflecting the orange, so it's absorbing the blue.
Oh, okay.
Okay.
Complementary.
Yep. Okay.
Okay.
So if we're using a red solution, we want to choose green light because that's what it's absorbing.
Okay.
Does that make sense? You gotta think on the opposite side of this. What you're gonna do is you are actually going to put your cuvette in, and you're gonna measure the absorbance. And wherever is the highest part of that peak, I think it's the highest. I'm gonna go back and read. Yeah. Then you're gonna choose that wavelength of light and gain the value. I've got it all in the directions for lab.
Good.
Okay.
Wait, so what? Will we see all the colors in the lab?
No.
Just one.
No, just the blues.
Yes.
Okay. So you're going to create one of these graphs here. Okay. A is the absorbance. This is the absorptivity constant. They have to give you that, or you have to calculate it from the slope of the graph. Okay. The path length then is usually 1 centimeter. So these cuvettes are 1 centimeter. And that's typical of cuvettes. Like that's kind of the industry standard. And then you've got your concentration. So this is the Beer-Lambert law. The A is the absorbance. This is your molar absorptivity constant. They would either have to give you that, or you would have to calculate it using the slope of the line. This, like I said, is usually 1 centimeter. And then your concentration. So a lot of times you will get 3 of these and you have to solve for the other one. The other thing that you can do is you can create, and this is what you're going to do in here, is you're going to create one of these with known concentrations. Then I am giving you an unknown. You've got to figure out what its absorbance is, and then you can plot that on the line here and see where it falls, and then that tells you the concentration. So if you know the absorbance of the unknown, you can go down to the x-axis, and that'll determine your concentration. And I have all of those steps in the lab showing you how to do it. Assuming we don't get a ransomware attack over the weekend and we're able to do the lab on Monday, as opposed to last year.
Wait, you
Was
didn't
this
get to
when
do
you-
the lab?
This was like.
This was the lab that I was trying to run then. And what I did was there's a way that you can jerry rig this with a cereal box, and you can make it happen with your cell phone and then do a little bit of calculus magic, and you can make this happen.
Calculus?
Yeah. And so we actually made it happen last year, but I was in tears a couple times. So, all right. Yep. So you're going to calibrate your spectrophotometer using that blank. Remember, the blank is just distilled water. And then you can use it from there. Okay, so based on this calibration graph, if the absorbance of the unknown was 0.34, what would be the molarity? So we're going to find 0.34 on here. We go over. Let's see, 0.34 would probably be about halfway in between this, right? So I don't know, about 3.2 maybe, something like that. Does that sound about right?
Yeah.
Okay. So that's all you have to do. Not too bad.
Wait, what?
Approximate where it would be on the graph, and this question is entirely.
Yeah, so
But
really.
it would be micro.
So
No,
3.2
never mind.
concentration.
All right, you good?
Yes, ma'am.
All right. So here they've given us this data. We are going to pick where this data comes in at the highest, because this is going to be the highest absorption. So what value is that? 620. Now I'm going to go back. Now that I have that in my mind, I'm going to go back to this guy. And I'm going to find 620 on here.
Yellow.
620 would fall into here. Okay. So orange.
620. Yellow is 590.
Oh, I read that. I don't even know what I read, but I read it as 6.
So orange is going to be absorbed. So what's going to be reflected? Blue. So that means the color of the solution would be blue.
So that's what we're gonna be absorbing, orange,
So for
right?
part A of that
Okay.
question, we would just say 620.
Good job. Okay.
Okay. Solution with an unknown amount of the same solute was prepared and graphed as shown. How is the new solution different from the first one? Lower absorption means what?
Oh, it's less concentrated.
Yep, less concentrated. Good.
Okay. Less.
All right. I need to give you your pre-lab then, which I've got somewhere.
Is it the pre-lab brass lab?
Yep. Oh, is it in your book?
Yes.
Oh, well, this one has an actual color wheel on it.
Yes.
so-
I would think so.
We'll take that one.
Do we have to memorize the wavelength?
No, they give you that. Wait, is it on our?
Where's Karina?
She skipped in school.
We gotta do attendance.
She drops.
She didn't
I
drop.
didn't give you
Watch
enough.
this.
Here.
She
Oh, no, I
dropped.
did. Emily. Oh, Emily's here?
Can I go to the van if you want any?
Huh?
I might go to the van if you want any.
Where's that?
That's
Bye,
fine.
Domino.
Thanks, but it doesn't matter.
Huh?
It's a coffee place.
Oh, by Luke's. Oh.
By the fence.
Just checking.
Wait, Evie loves going to.
Okay, the other thing that I
My
want you
parents don't
to
go.
do
I go like every day.
is I want this chart on this guy filled out. At this one right here. I want that guy filled out and ready to go for Monday. I also need to give you a piece of data on this lab. So if you turn to the second page here in the stapled portion, we need to fill in some blanks. The problem is that this varies from year to year, so that's why I didn't want to give it to you ahead of time. So number 4, the second number 4.
Okay.
Says I started with blank grams of brass. That is how much brass I started with.
Me too. Thank you.
We did not. 1 second.
It's a good number.
I'm going to get a tissue. Yay.
Okay, that you can fill in. This you have to do the lab for. So those blanks you'll have to fill in later. Okay, yep. So I want the pre-lab done by Monday. And I want this chart down here done by Monday. You guys should also know how to write or at least know what you're doing for the serial dilution. Well, my point is that if you guys don't have some of this done ahead of time, you may not have time next week to get everything done. So
How long is the lab?
it depends on how long it takes you to create this stuff. So step 1, you are creating 0.2 molar copper nitrate. I'm not telling you guys how to do this. Okay. So you're starting out with copper nitrate powder. You need to figure out how many grams of that you need. Okay. So how do we do that? Well, we need to know, we're figuring out we want 0.2 molar, right?
So you have to do a dilution.
You got to do moles over liters. Okay. So how much of this stuff, how much of that are you going to need? Well, you've got to figure out how much 0.2 molar you're going to need to be able to do all of this. And that's part of this chart. Okay. Once you've created your 0.2 molar from the copper nitrate, which you need to know the formula for that in order to figure out the molar mass of it. So if you don't know how to write copper nitrate down, that's the formula for it. Okay. You need to figure out how many moles you're going to need and how many liters.
Okay.
Once you have that done, once you have this made, then you can take this 0.2 molar. Okay. You're finding V1. You know that you are creating for the first one, what is its molarity? 0.15. So you do 0.15 here. How many milliliters are you making? 25, because that's your volumetric flask. Okay. And you solve for V1. That's going to tell you how many milliliters of 0.2 that you need. Okay. Once you get all of this calculated, then you'll know how many liters you need here.
I don't know, because I didn't think of where she was talking.
Does that make sense?
Yeah.
Then you need to do what with this value? I'm going to take this and I'm going to change it to, I need to do this equation again. Yep. And then I just keep repeating it for each additional concentration I need. I've done the unknown one. You don't need to do that. Okay? It's already made. It's already ready to go. Otherwise, I wouldn't know what's in black.
What's done?
Yeah, did you finish the
I'll read. Don't find them? My top drawer.
You did?
Not that top drawer. Middle top drawer.
How about, help you out with the package?
No, middle top. Top. Middle. Come here. Come here. Come here. Middle top. All right. Switching gears once again. Switch gears. Switch gears. Switch gears. And we are done with Unit 3 notes, you guys. You too, hon, thanks.
Following students, please report to the attendance office. David DeStefano and Javier Perez.